Hi, I'm Tarasha. Thanks for checking out our talk. This is our work on differentiable raycasting for self-supervised occupancy forecasting. The task we look at in this work is the following. Given a set of past bird's-eye view LiDAR sweeps aligned to a global coordinate frame, we want to output how the underlying occupancy of the scene evolves in the future, and given this future occupancy, what is the best motion plan that an autonomous vehicle or AV can take? In recent years, motion planning for AVs has been done with supervision from semantic labels such as object tracks and HD maps. In contrast to this expensive annotation-based supervision, several self-supervised approaches have emerged that use captured LiDAR sweeps to learn motion plans in an end-to-end manner, all at zero annotation cost. One such work learns an intermediate explainable representation for motion planning called egocentric free space. However, the change in egocentric free space at every time step is a complex transformation as it depends both on the position of the sensor in the environment and the motion of the dynamic scene elements. Let us look closely at this. Consider a scene S in which a sensor such as LiDAR is placed at a location Y. The green region shows how the egocentric free space would look like when rendered with a given scene and sensor parameters. Now, even when the entire scene remains static, and only the sensor changes its position, egocentric free space changes. The same is true when the sensor remains static, but only the scene moves. Therefore, egocentric free space conflates or is a function of sensor and scene motion. To simplify our problem, let us assume we know the future sensor motion. Then we only need to forecast the scene motion in order to forecast a viable AV trajectory. To do this, we adopt the neural motion planning architecture from prior work, and instead of directly predicting egocentric free space, we first predict a quantity that we hope encodes scene motion, and then we use the future sensor motion to raycast this quantity into egocentric free space, which we've already seen is self-supervisable. The crucial part of such a pipeline is that on training, the intermediate quantity indeed emerges into occupancy. For this reason, we call this representation emergent occupancy. With such a formulation, our pipeline easily factors out sensor motion from the scene motion, thereby reducing the complexity of our task. For this decoupling, differentiable raycasting with known ego poses is key. In fact, we relax our previous assumption of known ego poses and show that future ego motion is actually available both during training and testing. Quantitatively, we see that this gives much better egocentric free space forecasts when compared to the state-of-the-art on the NeoScenes dataset and the ONCE dataset across 4 metrics used by prior work. Qualitatively too, our free space forecasts are better than the state-of-the-art. Specifically, the bottom row shows well-defined objects even 3 seconds into the future. Let us now take a look at how this occupancy is used for downstream motion planning. We first compute occupancy cost maps, where a high cost is given to regions that are occupied and non-drivable. And we also predict imitation learning cost maps in which the cost is low in regions that are likely to be traversed by an expert. A combination of these cost maps is used to find the best candidate trajectory, which is the final prediction of our method. On the NeoScenes dataset, we see that emergent occupancy forecasting drastically reduces the box collision rate as compared to other self-supervised approaches. Here, we show the emergent occupancy, final cost maps, and the best motion plan predicted by our method. In the first example, our output motion plan decelerates the ego vehicle to avoid crashing it into the car ahead. In the second example, we output a motion plan that successfully navigates through an intersection. We additionally see that object shapes, tracks, and multiple futures emerge in our occupancy-like representation. For more experimental analysis of our method and details about the architecture, please refer to our paper. Thank you.